Imagine this traveller you didn't arrive here by accident. Something in the dark, something ancient guided you. What if the greatest archaeological discovery of our century isn't buried in any soil at all but drifting silently between the planets? A fragment of another star moving on a 1 in 20,000 trajectory that brushed past 3 worlds before we even noticed. Astronomers saw it accelerate without propulsion, a light that blinked once and was gone, a whisper hidden in the background radiation of our own cosmic neighbourhood. Stay a while, traveller, let's drift through the silence together. In the early hours of October 19th, 2017, an unassuming patch of sky in the constellation Cancer offered humanity a quiet revelation. At 2:20 a.m. the Pan-star's Snunbury. One telescope on Haleakala completed another routine scan, a field containing approximately 60,000 stars each, a reservoir of ancient photons that had travelled for millions of years before reaching the telescope's sensor. Nothing in that frame suggested urgency yet. Among the familiar points of light lay a subtle streak, an object reflecting sunlight in a way that did not match the gravitational behaviour of typical solar system bodies. Initially, the automated software classified the detection as a probable near-Earth asteroid. Such classifications are common. The solar system is filled with remnants of planetary formation, drifting in predictable elliptical orbits shaped by 4.5 billion years of gravitational evolution. But when Dr. Robert Werrick examined the data at the University of Hawaii, he noticed anomalous motion. The object's velocity was too high for any body gravitationally bound to the Sun, and its inbound trajectory originated from a direction inconsistent with established orbital families within the solar system. Early calculations revealed a striking result. The orbit possessed an eccentricity greater than 1, placing the object on a hyperbolic trajectory, a mathematical signature of an interstellar origin. The designation A 2017 U1 offered little insight into the object's significance, but within 48 hours additional observations confirmed that this was the first known visitor from beyond the Sun's gravitational domain. The astronomy community responded with unprecedented coordination. Telescopes around the world, Hubble Gemini VLT, redirected their schedules to capture every possible photon before the object faded into the cosmic background. In this collaborative effort, humanity treated the event not as an anomaly, but as an opportunity to observe physics unfolding from beyond our familiar planetary neighbourhood. It would later be named Oumuamua, a Hawaiian term meaning a scout or messenger from afar arriving first. The name proved fitting. As photometric data accumulated, the object revealed properties unlike any known asteroid or comet. Its brightness varied by a factor of 10 in each roughly 8-hour rotation period, implying an extreme aspect ratio. Models suggested an elongated shape, approximately 800 metres long and 80 metres wide, although alternative geometries such as a flattened disc-like structure were also consistent with the data. Regardless of the precise morphology, Oumuamua's geometry lay far outside the distribution predicted by standard solar system formation processes. More unusual still was its rotational state. Rather than spinning around a principal axis, Oumuamua exhibited non-principal axis rotation, a tumbling motion typically associated with recent collisional disturbance or heterogeneous internal structure. Despite this, the object showed no signs of structural fragmentation, implying considerable material strength. Spectroscopic measurements indicated a surface rich in irradiated organic compounds, imparting a reddish hue consistent with long-term exposure to cosmic rays during interstellar transit. However, the most scientifically intriguing property emerged as the object receded from the Sun. Precise astrometric measurements detected a non-gravitational acceleration of approximately 5×10⁶ sec-meso. Such accelerations are common in comets where sublimating volatiles generate recoil forces, yet Oumuamua displayed no coma, no tail, and no measurable gas emissions. Infrared data revealed no thermal excess that would indicate ongoing sublimation. If outgassing were responsible, it would require a mechanism that produced force without detectable byproducts, a scenario that challenged conventional cometary physics. To reconcile the anomaly, scientists proposed a spectrum of natural hypotheses: a volatile, poor comet with deeply buried ices, an aggregate of porous fractal material exhibiting enhanced solar radiation pressure, or even exotic hydrogen or nitrogen icebergs objects that could sublimate invisibly. Each model explained some subset of the data but required assumptions about formation environments or material properties that have not been observed elsewhere. As with many frontier discoveries, the data resisted convergence toward a single interpretation. Oumuamua remained observable for only 11 weeks. After that, its brightness fell below instrumental sensitivity, leaving a trail of unresolved questions. Yet in that brief interval, it accomplished something profound. It revealed that interstellar objects do not merely exist in theoretical models, they pass through our solar system silently on timescales that intersect with human observation. The discovery implied that interstellar material exchange may be far more common than previously estimated. If surveys can detect one such visitor during a short observational window, the galactic population of similar bodies must be immense. Oumuamua's passage established a new scientific paradigm. It marked the beginning of interstellar object astronomy, motivating the refinement of detection algorithms and the development of dedicated survey instruments. It also reminded us that cosmic discovery often begins not with dramatic events, but with a quiet deviation in a field of data, an unassuming streak of reflected sunlight that challenges existing frameworks and invites deeper inquiry. And in that invitation lies the central truth of the discovery: some mysteries are not obstacles but openings. Some signals are whispers meant only to be observed, and sometimes, traveller, it is enough to know that the universe still surprises us. Oumuamua's appearance did more than signal the arrival of the first known interstellar visitor. It exposed the limits of current planetary science. Once its unbound trajectory was established, the next challenge lay in deciphering its physical structure. Photometric data had revealed brightness variations by a factor of 10 and amplitude, far exceeding that of typical solar system bodies. Most asteroids exhibit modest light curve fluctuations since their shapes remain within predictable bounds, shaped by collisional evolution and gravitational relaxation. Oumuamua, by contrast, demanded an entirely different geometric interpretation. Models converged on two possibilities: an elongated spindle-like form, approximately 800 meters long and 80 meters wide, or a thin pancake-like geometry with similarly extreme proportions. Each scenario departed significantly from the known outcomes of natural formation processes. The tensile strength required to sustain such shapes over millions of years posed immediate questions. In familiar environments, bodies subjected to rotational torques and micrometeorite impacts tend toward fragmentation or compaction, not extension. To maintain such an aspect ratio through interstellar transit, the object would require either exceptional mechanical coherence or a formation environment rarely encountered in planetary systems. The rotational state deepened the puzzle. Instead of spinning around its principal axis with stable periodicity, Oumuamua exhibited non-principal axis rotation, a tumbling motion indicative of an uneven distribution of angular momentum. Such tumbling can result from relatively recent collisional events, yet no signs of structural breakup or loose debris accompanied its motion. Its persistence suggested an internally heterogeneous body capable of retaining complex rotation over extended timescales. This behavior alone placed Oumuamua at the edge of existing dynamical models for small bodies. Spectroscopic studies, while limited by the object's faintness, added further complexity. The surface exhibited a reddish spectral slope, consistent with long-term cosmic ray irradiation of organic-rich materials. But unlike typical comets that display vigorous outgassing when warmed by solar radiation, Oumuamua produced no detectable volatiles. No coma, no tail, no gas emission lines despite its close perihelion passage. Thermal models indicated that under solar heating, any near-surface ices should have sublimated and left measurable signatures. Their absence challenged conventional classifications. What emerged was a body with a composition reminiscent of irradiated organics, but a behavior inconsistent with either asteroidal inertia or cometary activity. Its outbound trajectory introduced the most contested property, a small yet statistically significant non-gravitational acceleration. In comets, asymmetric sublimation can generate measurable recoil forces, but without detectable outgassing, such an explanation strained credibility. This anomaly prompted a suite of natural hypotheses. Some researchers proposed that the object was composed of hydrogen ice, a material capable of sublimating invisibly. Yet hydrogen icebergs require formation in extremely cold molecular cloud environments and face survival challenges during interstellar travel. Others suggested nitrogen ice fragments originating from the surfaces of Pluto, like exoplanets, yet the volume of nitrogen required to populate interstellar space with such debris exceeded plausible planetary budgets. More intricate models envisioned fractal aggregates, highly porous structures, experiencing enhanced solar radiation pressure. These aggregates could produce acceleration without visible gas emission, but their fragility made ejection and long-term survival uncertain. No hypothesis successfully addressed all observational constraints. Instead, each explained one subset of data, while creating unresolved tensions elsewhere. This multidimensional mismatch underscored a deeper truth. Oumuamua belonged to a category of interstellar debris not yet formalized within planetary science. Its properties aligned only partially with familiar paradigms, suggesting that the diversity of material circulating through the galaxy is broader than the subset represented in our own solar system. The search for explanatory frameworks expanded accordingly. Some researchers revisited tidal disruption models, positing that a parent body might have been stretched by a close stellar encounter and subsequently fragmented into elongated shards. Others considered thermal fracturing near luminous stars or the erosive effects of prolonged interstellar dust collisions. Still others modelled how repeated cycles of heating and cooling could reshape surface layers over millions of years. Though each scenario offered conceptual pathways, none provided a fully coherent synthesis. Theoretical efforts increasingly acknowledge that the galaxy likely produces bodies through formation channels not yet captured in present datasets. When viewed in this context, Oumuamua's anomalies became less an exception and more an indicator of incomplete sampling. With only a single interstellar object observed in detail, statistical expectations remain fragile. The discovery of additional visitors may eventually reveal patterns, allowing comparative analysis rather than singular inference. What remains most significant is not any specific model, but the shift in scientific posture that the object demanded. Oumuamua required researchers to confront uncertainty directly, to recognize the provisional nature of existing assumptions and to expand the conceptual boundaries of small body physics. Its passage through the solar system lasted only weeks, yet its influence persists, reshaping the frameworks through which scientists interpret interstellar matter. Its legacy is not a definitive classification, but an invitation, an opening into a broader understanding of the galaxy's capacity to generate structures, materials, and trajectories beyond current expectation. In that sense, the object served as a reminder that the solar system is not isolated, but immersed in a dynamic cosmic environment, and within that environment, fragments from distant worlds will continue to arrive, each carrying signatures of their origins, each expanding the horizon of what planetary science must learn to explain. As Oumuamua receded into the outer solar system, its brief observational window closed, but its scientific influence persisted, catalyzing an unprecedented re-evaluation of how interstellar objects are detected, classified, and interpreted. For decades, planetary scientists relied on statistical models predicting that such visitors should be exceedingly rare, perhaps one detectable object per century. Yet the very detection of Oumuamua implied that these estimates were fundamentally incomplete. If the first such object appeared within the short operational lifespan of modern surveys, the logical inference was that the underlying population must be vastly larger than anticipated. This discrepancy between prediction and observation initiated what researchers began calling the interstellar population problem. The mathematics were straightforward but troubling. Survey telescopes such as Pan-STARRS and the Catalina Sky Survey have limited spatial and temporal sensitivity. They detect only a small subset of objects passing near Earth, and only if the geometry and illumination conditions align favourably. If a single interstellar object was detected by instruments with such constraints, the true galactic population must be immense, likely orders of magnitude greater than earlier models suggested. Monte Carlo simulations incorporating observational biases and survey limitations indicated that thousands of similar objects may pass through the inner solar system each year, nearly all too faint or too distant to be observed. This statistical implication transformed Oumuamua from an anomaly into a natural consequence of a far more dynamic galactic environment, the realization that our solar system exists within a continuous flux of interstellar debris reshaped multiple fields of inquiry. Planetary formation models, which previously emphasized local processes, now had to incorporate mechanisms for exporting material across stellar systems. Ejection events occur when gravitational interactions between giant planets and planetesimals impart sufficient energy to unbind objects from their host stars. These processes are common in young planetary systems undergoing migration, but the number necessary to populate interstellar space at the inferred density appeared implausibly high unless the galaxy contained additional unmodelled ejection pathways. This led researchers to revisit scenarios involving stellar evolution, binary interactions, and cluster dynamics. Stars forming in dense clusters interact gravitationally, exchanging bodies and perturbing orbits in ways that can accelerate debris into interstellar trajectories. As stars separate from their birth clusters and migrate across the galaxy, the debris they have ejected disperses, contributing to a diffuse isotropic population of small interstellar bodies. Additionally, the death of stars, whether via supernovae, planetary nebulae, or asymptotic giant branch winds, can release substantial material into the surrounding medium. Each mechanism produced debris with distinct compositional signatures, implying that interstellar objects arriving in the solar system represent a broad and varied sampling of galactic astrophysical history. The diversity of potential origins underscored another emerging field, the comparative study of interstellar object chemistry. Although data for Oumuamua were limited, its reddish spectral slope and volatile depleted surface suggested long exposure to cosmic rays in the interstellar medium. The absence of detectable ices and the presence of refractory materials implied a body that had either lost its volatiles through prolonged irradiation or formed in an environment with inherently low volatile content. This raised questions about whether Oumuamua was a typical representative of interstellar debris or a rare, heavily processed specimen. Without comparative data, classification remained speculative. That comparative data arrived unexpectedly in 2019 with the discovery of 2I Borisov, the second confirmed interstellar object. Its properties contrasted sharply with those of Oumuamua. Whereas Oumuamua exhibited no coma and no discernible sublimation, Borisov behaved like a conventional comet, demonstrating active outgassing, a clear tail, and a composition rich in carbon monoxide at concentrations far exceeding those in solar system comets. This chemical divergence provided the first empirical support for the hypothesis that interstellar objects represent a wide compositional spectrum reflective of varied formation environments. The contrasting behaviours of the two visitors revealed that interstellar space does not deliver a homogeneous population, but rather a mosaic of planetary fragments shaped by diverse astrophysical histories. The presence of these differences compelled planetary scientists to reconsider how they conceptualized interstellar debris. Instead of imagining a single representative type, researchers began to model an entire distribution of interstellar object properties spanning volatile-rich comets, volatile depleted rocky fragments, irradiated aggregates, and bodies shaped by tidal or collisional processes in foreign stellar systems. Oumuamua and Borisov became the first two data points in a projected continuum that future detections would gradually populate. Their combined dataset also informed astrobiological inquiries. If interstellar objects frequently enter planetary systems, they could facilitate the transfer of organic compounds and possibly prebiotic chemistry across stellar environments. While the survival of biological material during interstellar transit remains contested, the mechanisms for distributing complex molecules appear robust. Irradiated organics detected on icy bodies within the solar system demonstrate that cosmic rays can synthesize stable carbon-rich materials. If similar processes operate on interstellar objects, then molecular building blocks of life may circulate through the galaxy far more widely than previously believed. This prospect rekindled scientific interest in panspermia, not as an extraordinary speculation, but as a plausible component of galactic chemical evolution. The recognition of this interconnectedness prompted the development of new research infrastructures. Telescope surveys began integrating algorithms optimized for identifying hyperbolic trajectories. Planning for rapid response space missions intensified with the aim of intercepting future interstellar visitors before they recede from observational reach. The Vera C. Rubin Observatory, with its high-cadence all-sky imaging capabilities, emerged as a cornerstone of this next era, expected to detect dozens of candidates per year once fully operational. In parallel, spectroscopic facilities were reconfigured to perform near-instantaneous follow-up observations. What emerged from these efforts was not merely an expanded dataset, but a conceptual shift to the view of the solar system as a porous boundary rather than an isolated domain. Instead of a static environment that occasionally encounters rare interstellar objects, the inner solar system appears to be a transit corridor through which diverse materials continuously flow. This recognition reframed planetary science within a broader galactic context, emphasizing that local observations are inseparable from the dynamical processes governing the Milky Way as a whole. Through this lens, Oumuamua no longer represented an outlier, but the first visible member of a vast unseen population. Its irregularities, geometric, rotational and chemical, signalled the multiplicity of formation channels and evolutionary pathways operating across the galaxy. The scientific questions it raised remain open, but the framework it reshaped endures, guiding the interpretation of every new object that crosses the Sun's gravitational threshold. The arrival of a second interstellar visitor, 2I Borisov, offered a rare opportunity for comparative analysis and confirmed that the galaxy produces not one archetype of interstellar material, but a diverse population shaped by numerous astrophysical environments. Yet while Borisov behaved as a chemically active comet consistent with volatile rich formation regions, the discovery of a third interstellar object expanded the emerging dataset in even more instructive ways. In July 2025, the Atlas survey identified a faint point of light moving at an anomalously high velocity through the southern sky, an object later known as 3I Atlas. Preliminary orbital solutions revealed an eccentricity approximating 6, placing it on an extremely open hyperbolic trajectory. More significantly, unlike Oumuamua, 3I Atlas was detected incoming, affording astronomers months of observational lead time rather than weeks. This advance notice transformed the scientific approach to studying interstellar visitors. Instead of scrambling to coordinate multi-instrument campaigns, researchers mobilized established protocols designed in the wake of Oumuamua. Telescopes were scheduled preemptively. Spectroscopic campaigns were initiated at multiple wavelengths. High-resolution imaging systems were synchronized to track subtle changes in the object's coma and nucleus. Whereas the first visitor forced reactive observation, the third enabled systematic study, allowing scientists to construct a detailed temporal evolution of its physical characteristics across heliocentric distance. Initial imaging revealed activity well before the object reached the inner solar system. Even at distances comparable to Jupiter's orbit, 3I Atlas exhibited a faint coma approximately 25-50 kilometers across, suggesting a reservoir of highly volatile ices capable of sublimation at relatively low temperatures. Such behaviour contrasted sharply with Oumuamua's inert surface, but aligned with predictions for comets formed in the outer regions of foreign stellar systems. Spectroscopy soon revealed a composition dominated by silicate minerals and organic-rich compounds with isotope ratios indicating formation around a star with metallicity distinct from the Sun. These subtle chemical offsets provided new constraints on the diversity of stellar nurseries, contributing to the interstellar debris field. The rotational characteristics of 3I Atlas also offered insight into its internal structure. Light curve analyses indicated a rotation period of roughly 29 hours, significantly slower than either Oumuamua or Borisov. The amplitude of the light curve suggested a moderately elongated shape, without the extreme proportions inferred for Oumuamua. This placed 3I Atlas within a more conventional geometric regime, implying that highly elongated bodies like Oumuamua may represent rare outcomes of extreme processes rather than typical interstellar morphology. Across these early measurements, 3i Atlas appeared to embody an intermediate state between the volatile rich behaviour of Borisov and the volatile depleted, structurally anomalous form of Oumuamua. Yet even in its relative normalcy, the object introduced new complexities. As it approached solar perihelion, the rate and spectral characteristics of its outgassing fluctuated in ways not entirely correlated with incident solar flux. Such variations suggested spatial heterogeneity in surface composition or internal layering, possibly remnants of formation within a circumstellar disk exhibiting radial chemical gradients. This heterogeneity provided new clue interstellar objects could preserve compositional stratification, reflective of their natal environments, offering a unique opportunity to probe protoplanetary disk chemistry beyond the solar system. The directional arrival of 3i Atlas also carried theoretical significance. The object approached from the constellation Sagittarius at an inclination nearly perpendicular to the ecliptic plane. When combined with the inbound directions of Oumuamua and Borisov originating near Lyra and Cassiopeia, respectively, an emerging pattern became clear. Interstellar visitors entered the solar system from widely separated regions of the sky with no preferred direction. Such isotropy implied a galactic population well mixed by gravitational diffusion, consistent with models of long-term orbital evolution within the Milky Way's differential rotation. This distribution also refuted earlier speculations that interstellar debris might exhibit alignment with the Sun's motion through the local interstellar medium. The extreme velocity of 3i Atlas required additional analysis. At approximately 61 km relative to the Sun, it travelled significantly faster than expected for objects ejected solely by planetary interactions within typical stellar systems. Such velocity magnitude suggested either an origin in a dynamically energetic environment, perhaps involving stellar encounters, post-main sequence mass loss, or perturbations within dense stellar clusters, or an exceptionally long interstellar trajectory, during which minor gravitational influences accumulated over millions of years. Simulations tracing the object's past trajectory revealed that identifying a specific parent star was nearly impossible. Gravitational encounters with multiple stars at various epochs erased any deterministic link to its birthplace. Instead, astronomers could infer only general kinematic properties pointing toward possible origins in the galactic thick disk. From a population perspective, the detection of 3 interstellar objects within 8 years fundamentally altered estimates of interstellar small body density. Statistical recalibrations indicated that large objects hundreds of meters to kilometers in scale might pass through the solar system several times per decade, with smaller objects arriving even more frequently. Such density implied that the Milky Way efficiently exports debris from planetary systems into the interstellar medium, reshaping theoretical expectations for material exchange at galactic scales. The implications extended into astrobiology, planetary formation theory, and even cosmic chemical evolution. Astrobiologists noted that repeated encounters with chemically diverse interstellar bodies could have contributed organic precursors to early Earth, and potentially to other worlds as well. While the survival of biological macromolecules during interstellar transit remains uncertain, the transport of carbon-rich materials appears robust. Objects like Borisov and 3i Atlas carry signatures of organic chemistry shaped by irradiated ice's materials, with demonstrated capacity to seed planetary surfaces with complex molecules. In parallel, the broader astronomical community acknowledged that the accumulation of interstellar visitors represented a new empirical dataset unparalleled in scientific history. For the first time, researchers could study materials formed under foreign stellar conditions without launching missions to distant stars. Each object delivered direct samples of protoplanetary environments shaped by different elemental abundances, thermal histories, and dynamical processes. In this expanding framework, 3i Atlas emerged not merely as an observational target, but as a catalyst for a new era of comparative interstellar planetology. Its behaviour illustrated the spectrum of possible outcomes for bodies migrating between stellar systems, and underscored the significance of sustained observation across the inbound trajectory. The object's passage reaffirmed a central conclusion: the solar system is permeable, not isolated a node within a galaxy-wide circulation of matter. originating from countless worlds whose histories precede and surpass our own. As 3 Atlas progressed toward the inner solar system, its trajectory became a focus of sustained dynamical analysis, revealing patterns that further expanded humanity's understanding of how interstellar objects traverse the galaxy. Unlike bodies gravitationally bound to the Sun, which follow elliptical orbits conforming to Keplerian constraints, 3I Atlas moved along a sharply hyperbolic path with an eccentricity close to 6. Such a trajectory indicated not merely escape velocity, but substantial surplus kinetic energy, confirming its origin in an external stellar system and suggesting a complex dynamical history prior to its arrival. The reconstruction of its past trajectory required integrating gravitational influences from the Sun, major planets, and the galaxy's local stellar population. Astronomers employed N-body simulations incorporating the galactic potential local stellar density and estimates of stellar encounters over million-year timescales. Yet these backward integrations diverged rapidly. Even slight uncertainties in initial conditions produced exponentially widening positional variances due to cumulative gravitational perturbations. This chaotic behavior rendered identification of a specific parent star infeasible beyond a few million years, placing 3I Atlas among the category of interstellar bodies whose precise origins remain statistically but not deterministically constrained. Despite this, modelling efforts revealed characteristic features of its possible birthplace. Its high inbound velocity combined with the isotropic arrival direction suggested origins in the galactic thick disk or a dynamically active star-forming region. Such environments exhibit higher velocity dispersions and more frequent gravitational interactions capable of ejecting planetesimals at the speeds observed. Some simulations indicated that 3I Atlas may have been expelled during early planetary system formation when migrating. Giant planets destabilize smaller bodies. Others favoured ejection scenarios involving mass loss phases of evolved stars, particularly asymptotic giant branch winds or post-main sequence expansion where gravitational restructuring destabilizes planetary orbits. The potential involvement of such varied astrophysical context illustrated a key realization. Interstellar objects do not represent a single evolutionary pathway, but rather a composite record of galactic processes. Each visitor encodes information about its natal environment, formation chemistry, and dynamical ejection mechanism. Through this lens, 3I Atlas served as a data point in a wider distribution reflecting cumulative influences from stellar neighbourhoods shaped by metallicity gradients, radiation fields, and dynamical histories distinct from those of the Sun. As it neared perihelion, 3I Atlas offered deeper insight through its evolving physical behaviour. Solar heating amplified its outgassing activity, producing a coma and tail whose morphology fluctuated subtly across rotational phases. High-resolution imaging suggested anisotropic emission patterns indicating non-uniform distributions of volatile species. Such heterogeneity pointed toward compositional layering within the nucleus, possibly reflecting radial gradients in its formation disk. These gradients, preserved through millions of years of interstellar transit, presented rare opportunities to study primordial chemical stratification from a foreign stellar system. Spectroscopic observations recorded volatile signatures, including water vapor carbon-bearing compounds and trace organic molecules. The isotope ratios of hydrogen and oxygen deviated from solar system baselines, implying formation around a star whose protostellar cloud possessed a distinct enrichment history. These deviations aligned with expectations for stars in regions of the galaxy, shaped by different supernova contributions, reinforcing the view that interstellar objects serve as natural probes of galactic chemical evolution. As data accumulated, astronomers compared the 3 confirmed interstellar visitors in search of unifying principles. Oumuamua exhibited extreme elongation, tumbling rotation, and non-gravitational acceleration without detectable volatiles. Borisov behaved like a hyperactive comet enriched in carbon monoxide and displaying sustained sublimation. 3I Atlas occupied an intermediate space comet-like in structure, but chemically distinct. Taken together, these contrasts demonstrated that interstellar objects span a compositional and morphological spectrum far broader than expected from models based solely on solar system analogues. The The emerging comparative framework suggested that the galaxy disperses material from planetary systems with remarkable efficiency. Gravitational instabilities, stellar encounters, and late-stage stellar evolution collectively contribute to a substantial population of free-floating small bodies. These bodies once ejected travel through galactic orbits shaped by the Milky Way's differential rotation, interacting only weakly with the sparse interstellar medium. Their survival over millions of years indicates that many possess sufficient structural resilience to endure cosmic radiation, micrometeorite impacts, and thermal cycling. 3 Atlas also underscored the significance of early detection. With months of observational data rather than days or weeks, scientists could construct detailed temporal profiles of its sublimation dynamics, rotational modulation, and chemical evolution across heliocentric distance. Such longitudinal datasets enable constraints on nucleus size density, estimates thermal inertia, and the spatial distribution of volatiles. Moreover, coordinated observations across multiple wavelengths provided a multi-layered view of its evolving coma, offering insights into gas release mechanisms and dust-to-gas ratios. These detailed observations fed into broader models of interstellar object survivability. The detection of active sublimation at large heliocentric distances suggested that some interstellar bodies retain significant volatile content, despite prolonged exposure to interstellar radiation fields. Such retention challenges earlier assumptions that multi-million-year journeys necessarily strip objects of their ices. Instead, it appears that structure composition and initial conditions strongly influence long-term stability, implying that a substantial fraction of interstellar objects may arrive with intact chemical inventories. At a larger conceptual scale, 3I Atlas contributed to a shifting paradigm regarding the solar system's place within the galaxy. Rather than a system visited only rarely by foreign materials, the data now support a model in which interstellar bodies pass through with regularity. Their trajectories crisscross planetary space sampling gravitational fields, while offering momentary opportunities for observation before they return to the stellar background. This dynamic flux positions the solar system not as an isolated domain, but as an open system participating in the continuous galactic circulation of matter. In this expanded view, each interstellar visitor becomes not an anomaly, but a messenger, one carrying physical evidence of processes that shaped distant planetary systems long before humanity existed to observe them. Their varied compositions, morphologies, and dynamical histories reflect the diverse astrophysical environments of the Milky Way, providing natural laboratories for studying small body physics beyond the solar context. And as detection capabilities expand, the frequency of such encounters will likely increase, enabling more robust statistical interpretations and deeper exploration of galactic material diversity. As observational campaigns on 3I Atlas intensified, scientists began comparing its growing dataset with the accumulated information from the 2 prior interstellar visitors, attempting to discern population-level characteristics, rather than treating each object as an isolated anomaly. This comparative effort revealed not only diversity, but also emerging patterns that hinted at deeper astrophysical principles governing the formation, evolution, and distribution of interstellar bodies. Each visitor, Oumuamua, Borisov, and Atlas, presented a distinct chemical and dynamical personality, yet together they illustrated the wide parameter space occupied by materials circulating through the galaxy. Among the most instructive differences lay in their outgassing behaviours. Oumuamua exhibited no detectable volatiles, despite experiencing solar heating sufficient to sublimate common ices. Its surface remained inert, suggesting either extreme volatile depletion or a refractory crust created by prolonged exposure to cosmic radiation. Borisov, by contrast, displayed vigorous activity throughout its passage, showing water vapour cyanide and particularly high concentrations of carbon monoxide, far exceeding typical values for solar system comets. This abundance of highly volatile species implied formation in exceptionally cold regions of its natal disk. Atlas presented an intermediate state active sublimation that began at unusually large heliocentric distances, possibly indicating a mixture of both highly volatile and more refractory ices. The 3 visitors thus spanned a continuum from inert rocky fragments to volatile-rich comets, highlighting the heterogeneity of materials produced during planetary system formation across the Milky Way. chemical diversity extended beyond volatiles. Spectroscopic analyses revealed meaningful variations in elemental and isotopic ratios. In Atlas, deviations in hydrogen and oxygen. Isotopes suggested formation around a star with different levels of heavy element enrichment relative to the Sun. Such differences reflected distinct stellar nucleosynthesis histories, influencing the composition of protoplanetary disks. Similarly, Borisov's carbon monoxide enrichment pointed toward outer disk regions, shaped by temperature gradients unfamiliar in our own solar system. Oumuamua's spectral slope consistent with irradiated organics implied long-term exposure to the interstellar medium. Taken together, these findings demonstrated that interstellar objects serve as chemical tracers carrying signatures of diverse protoplanetary environments and offering indirect access to astrophysical processes far beyond observational reach. Rotational characteristics provided another dimension of comparison. Oumuamua's complex non-principal axis rotation suggested either recent perturbation or structural heterogeneity, while Borisov maintained a comparatively stable spin state, typical of conventional comets. Atlas rotated more slowly with a period of roughly 29 hours and displayed light curve modulations consistent with moderate elongation. These differences underscored the influence of internal structure, collisional history, and past dynamical interactions on the rotational states of interstellar bodies. Because such states evolve slowly in the sparse interstellar medium, they preserve information about events preceding ejection. The rotational diversity therefore offered clues to the mechanical histories of their parent systems. The growing dataset also prompted reconsideration of the mechanisms responsible for ejecting material into interstellar space. While gravitational scattering by giant planets remains a well-established source of unbound debris, the required ejection rates to explain observed interstellar object densities exceeded predictions based solely on solar system analogues. This discrepancy suggested a broader range of ejection pathways. Dynamical instabilities during early system formation, particularly in systems containing multiple giant planets, could expel large numbers of planetesimals. Stellar evolution processes, including mass loss during red giant phases, could destabilize entire planetary architectures, releasing bodies into interstellar trajectories. Dense stellar clusters where stars form in close proximity promote frequent gravitational interactions that can eject objects more efficiently than isolated systems. Additionally, cataclysmic events such as supernovae can contribute to the population of high-velocity debris by disrupting young planetary systems. The combination of these mechanisms operating across billions of years likely populates the interstellar medium with a complex mixture of materials reflecting multiple astrophysical origins. This recognition prompted renewed interest in how interstellar objects preserve evidence of galactic chemical evolution. Each body contains isotopic ratios influenced by the cumulative history of stellar nucleosynthesis within its formation region. Because different parts of the Milky Way undergo varying levels of chemical enrichment, interstellar objects act as messengers carrying localized chemical signatures across vast spatial scales. Their compositions thus provide empirical constraints on models of galactic evolution, bridging the gap between stellar spectroscopy and planet formation studies. As more detailed analyses of Atlas accumulated, researchers began using the combined dataset from all three visitors to characterize the statistical distribution of interstellar object properties. Variations in morphology, composition, and activity patterns suggested a broad but continuous population distribution, rather than discrete categories. The diversity likely reflects the wide range of protoplanetary disk conditions found throughout the galaxy, influenced by local metallicity, temperature gradients, stellar mass, and disk lifetime. This distribution undermined earlier assumptions that interstellar objects might resemble the average properties of solar system comets or asteroids. Instead, it indicated that the solar system's small bodies represent only a narrow slice of a much larger galactic inventory. Such realizations had significant implications for future observational strategies. Because interstellar objects vary widely in brightness activity, and composition detection algorithms must be capable of identifying both faint inert bodies, like Oumuamua, and bright active comets like Borisov, the need for multi-wavelength characterization became even clearer. Visible light photometry alone could not distinguish between compositionally distinct objects, infrared spectroscopy radio observations and high-resolution imaging were necessary to build robust profiles. The development of rapid response observational networks ensured that whenever a new interstellar candidate was detected, a coordinated campaign could extract maximal scientific value before the object faded. These evolving strategies were informed by a fundamental shift in perspective. Interstellar objects were no longer treated as rare anomalies, but as routine components of the solar system's dynamical environment. Their recurring presence redefined the solar system not as an isolated gravitational domain, but as an open system embedded within a larger galactic ecosystem. Their trajectories, compositions, and behaviours collectively illustrated ongoing exchanges of matter between stellar systems, exchanges that have likely occurred for billions of years. In this broader context, the scientific significance of interstellar visitors transcended their individual peculiarities. They constituted a moving archive of processes shaping planets, disks and stars across the Milky Way. Each object provided a sample of material from a region of space, unreachable by any spacecraft offering direct evidence of conditions beyond the Sun's immediate neighbourhood. Through such visitors, the galaxy revealed itself not as a distant background, but as an interconnected system, its distant worlds linked through the slow circulation of matter carried by unbound bodies drifting between the stars. As the comparative framework for interstellar visitors matured, the effort to extract deeper principles from their behaviour shifted toward the analysis of signals buried within observational noise. The increasing precision of photometry, spectroscopy, and astrometry generated datasets filled with subtle anomalies, minute fluctuations in brightness, asymmetric line profiles, rotational irregularities, and non-gravitational accelerations. These features were rarely dramatic, yet each carried encoded information about the physical structure, thermal state, and evolutionary history of the objects. For astronomers, the challenge became not simply to catalogue such deviations, but to determine whether they represented intrinsic geological processes, environmental interactions, or signatures of previously unrecognised astrophysical mechanisms. With 3 interstellar visitors now studied in detail, scientists found themselves confronting a paradox. The more data they acquired, the more the universe revealed its complexity. Central to this growing sophistication was the realization that noise itself was not merely a limitation, but a diagnostic tool. Variations once dismissed as observational errors could upon closer analysis yield insights into surface morphology, compositional heterogeneity, or microfragment shedding. In the case of 3i Atlas, the early onset of outgassing generated fluctuating coma brightness that initially appeared chaotic. Yet high-cadence photometry revealed periodic modulation, synchronized with the object's rotation, suggesting localized volatile reservoirs exposed episodically as the nucleus turned. This pattern stood in contrast with ʻOumuamua's nearly featureless light curve noise, which lacked the stochastic flickering typical of active comets. The absence of sublimation signatures, even at perihelion, strengthened the hypothesis that its crust was either unusually refractory or shaped by long-term irradiation that removed surface volatiles entirely. Borisov offered a third profile: erratic bursts of activity that hinted at compositional stratification within its nucleus. These distinct noise signatures thus formed a comparative triad demonstrating how interstellar objects encode thermal histories within the microstructure of their light. Spectral noise became equally instructive. For Atlas, the intermittent appearance of faint organic emission bands indicated transient release of complex carbon-bearing molecules, likely trapped within amorphous ices that underwent phase transitions as the nucleus warmed. In Borisov's CO-dominated spectra suggested formation in a region of its parent disk beyond the CO ice line, where temperatures were far below those typical of solar system comet nurseries. Meanwhile, the near-featureless spectrum of Oumuamua spoke to its heavily processed surface, its original mineralogy concealed beneath layers of radiation-generated tholins. Through comparative analysis, astronomers realized that spectral irregularities, once considered artifacts of weak signal, were instead fingerprints of formation environments located light years apart. Dynamical signals provided another layer of complexity. Oumuamua's anomalous acceleration rose above background noise only through meticulous residual analysis of positional data across multiple observatories. The absence of corresponding coma signatures forced reconsideration of the processes capable of producing such a force. Hypotheses range from radiation pressure acting on an unusually thin object, to undetected sublimation of hypervolatiles, to thermal recoil, forces arising from asymmetric heat redistribution. Borisov's trajectory, in contrast, adhered closely to models of standard cometary outgassing. Atlas, with its rapidly evolving coma, displayed subtle non-gravitational dynamics, reflecting both solar heating and rotational modulation. The diversity of these behaviours demonstrated that no single mechanism governed the motion of interstellar objects. Instead, each body carried a trajectory shaped by its unique composition structure and thermal response. As datasets expanded, researchers began integrating multiple noise domains, photometric, spectroscopic, astrometric, into unified interpretive frameworks. This multimodal approach revealed correlations previously unnoticed. Objects with highly processed surfaces such as Oumuamua exhibited smoother rotational noise signatures consistent with homogeneous crusts lacking active venting. Bodies rich in volatiles such as Borisov and Atlas showed anti-correlations between gas production rates and rotational stability, suggesting feedback loops wherein sublimation torque subtly altered angular momentum distribution. Through such connections, noise evolved from an observational hindrance into a gateway for decoding the internal physics of interstellar objects. These analytical advances fed into broader theoretical questions about population diversity across the galaxy. If the noise characteristics of the three visitors represented only a small sampling of a vastly larger distribution, then the dynamical and compositional variance among unobserved interstellar bodies might be extraordinary. Statistical inference models suggested that the underlying population likely encompasses objects ranging from nearly isotropic crystalline fragments to volatile-rich aggregates with porous internal structures. The implications extended beyond planetary science into astrophysics. The diversity of small bodies reflects the diversity of stars' disks and environmental conditions that shaped them. Thus, through the faintest signals, astronomers glimpsed the structural and chemical heterogeneity of planetary nurseries spread across the Milky Way. At the same time, researchers recognized that the extraordinary sensitivity required to interpret such subtle noise approached the threshold at which natural variability blended with potential technological signatures. While no artificial signals had been identified, the methodologies developed particularly for disentangling weak systematic anomalies from stochastic noise were directly applicable to the search for engineered structures or energy distributions inconsistent with natural processes. By learning to hear the quietest fluctuations in interstellar visitor data, astronomers inadvertently refined the tools that might one day detect genuine techno-signatures. As observational campaigns continued, the scientific community developed a growing appreciation for the idea that the cosmos communicates primarily through nuance. Major discoveries did not emerge from explosive revelations, but from careful interpretation of tiny perturbations. A fractional magnitude shift, a spectral line broadened by an extra few milliards seconds, a deviation in trajectory smaller than a human hair projected across millions of kilometers. These microsignals, once dismissed as noise, became the foundation of a new discipline, one that treated each interstellar visitor as a multidimensional data set whose faintest features carried astrophysical meaning. In this way, the study of interstellar visitors matured into a practice of scientific listening. The galaxy, through its wandering fragments, spoke in whispers that required patience, precision, and humility to decipher, and each new visitor carried its own quiet message encoded not in bold signatures but in the fragile details suspended at the threshold of detection reminders that the universe rarely announces its truths loudly, but reveals them gently for those prepared to hear. As the comparative analysis of interstellar visitors deepened attention, gradually shifted toward the emerging probability problem, a quiet contradiction between what had been predicted and what the universe was now revealing with disarming frequency. For decades, theoretical models assumed that interstellar objects were statistical rarities, drifting sparsely through the galaxy like isolated relics of ancient planetary formation. Early calculations estimated that a detectable visitor should pass through the inner solar system perhaps once every century, if not once in several. Yet within a single decade, three objects of wholly different character, Oumuamua, Borisov, and through our Atlas, had presented themselves in succession. Their arrival rate was not merely surprising, it was mathematically inconsistent with long-standing expectations, and so astronomers found themselves confronting a quiet, unsettling question. Had the galaxy always been this crowded, or had humanity simply learned to look at precisely the moment when the sky began to speak more clearly? The revised probability estimates began with a straightforward observation: detection is a function of awareness as much as abundance. Older sky surveys lacked the cadence, sensitivity, and automated pipelines required to detect small, fast-moving interstellar bodies. The success of modern surveys therefore could not be attributed solely to an increase in visitor frequency, but rather to the maturation of observational infrastructure. Yet even after accounting for this shift, after adjusting models to reflect improvements in photometric depth, sky coverage, and computational filtering, the detection rate remained anomalously high. Statistical reconstructions showed that for 3 confirmed visitors to have been detected in 8 years, the true population density of interstellar objects must exceed previous estimates by 2 to 3 orders of magnitude. The interstellar medium, once imagined as a sparse expanse, now appeared to be populated by countless fragments, migrating between stars as naturally as dust carried along a river's current. The implications reached far beyond simple enumeration. If such a vast population existed, then ejection events in planetary systems must be far more common or far more efficient than classical models predicted. Planetary migration, gravitational scattering, stellar encounters, and tidal disruptions could all contribute to the release of debris into interstellar space, but prior simulations treated these mechanisms as rare or episodic. Now, the mathematics suggested that ejection must be a routine process, operating across millions of star systems, each contributing a steady outflow of small bodies to the galactic environment. In this view, the Milky Way resembled a complex interconnected chemical reactor, with materials from one stellar nursery ultimately drifting into the gravitational reach of another. Interstellar objects, far from being exceptional, became part of a larger metabolic cycle of galactic evolution. Monte Carlo models refined this emerging perspective by integrating the distribution of stellar types, planetary architectures, and encounter frequencies across the galactic disk. Researchers produced synthetic populations of interstellar debris. Even under conservative assumptions, the simulations predicted tens of trillions of objects larger than 100 meters permeating the galaxy. Most would remain undetected, too faint, too fast, or too distant, but their cumulative gravitational influence and occasional alignment with our observational window made their presence statistically inevitable. In this framework, the arrival of 3 visitors in less than a decade no longer seemed improbable. Instead, it became an expected consequence of living in a galaxy alive with dynamical exchange. This shift in understanding required a similar shift in epistemology. The older image of the universe, empty, silent, sparsely populated with wandering remnants, had been replaced by a dynamic vision of ceaseless motion. Small bodies once bound to their parent stars travelled on million-year odysseys shaped by gravitational resonances, stellar winds, and tidal interactions. Some originated during the violent birth throes of planetary systems. Others were ejected by close encounters with migrating giants. Still others emerged from cataclysmic disruptions, supernovae, stellar mergers, or even the gravitational collapse of wide binary systems. Over cosmic time, these processes populated the interstellar medium with a vast heterogeneous collection of fragments. A planetary system drifting quietly through the galactic disk could not help but intersect with this ancient flow. Yet the most intriguing aspect of the probability problem was not abundance, but implication. If interstellar visitors arrived frequently, then the Earth had been encountering such objects for billions of years. Most would have passed unnoticed. Some may have deposited exotic organics, or altered the distribution of isotopic ratios in prebiotic environments. A few might even have impacted the planet, contributing material distinct from anything produced within the solar system. The line between endogenous and exogenous chemistry, already blurred, grew softer still. The building blocks of life on Earth, long believed to have formed primarily within the protoplanetary disk, might instead reflect contributions from distant stellar lineages. This insight extended naturally into astrobiological speculation. If organic compounds could survive interstellar transit, and evidence increasingly suggested they could then, life's precursors might circulate through the galaxy in patterns governed not by biology, but by orbital mechanics. The probability problem thus intersected with theories of panspermia, transforming them from fringe conjectures into testable frameworks. The distribution of interstellar visitors became a proxy for the distribution of life-bearing material, and the frequency of their arrival shaped statistical expectations for the emergence of biology throughout the Milky Way. In the quiet of observatories, researchers reflected on what this shift truly meant. The galaxy was not a static arena of isolated star systems, but an open network of exchange in which matter flowed continuously across light years and epochs. Interstellar visitors were not anomalies, they were evidence of the galaxy's connective structure, its unseen currents, its long memory. And perhaps observers mused the real improbability had never been their arrival, but the centuries during which humanity watched the sky without realizing how often it was being visited. As the probability frameworks evolved, another question resurfaced with quiet persistence, the kind that returns not with urgency, but with the slow gravity of an unsolved equation. If interstellar objects drifted through the solar system far more frequently than once believed, and if these visitors carried the chemical signatures of distant worlds, then what did this abundance imply for the long-standing paradox articulated by Enrico Fermi? Where is everybody, he asked, confronting the contradiction between the statistical likelihood of extraterrestrial intelligence and the apparent absence of evidence? Yet now, under the soft glow of new observations, the paradox seemed to shift. Perhaps the universe had not been silent at all. Perhaps humanity had merely misunderstood the language in which the cosmos spoke. In classical formulations, the Fermi paradox assumed that interstellar space was largely empty, that physical travel between stars required extraordinary energy, and that communication across the gulf of light years would rely primarily on electromagnetic signals, a medium that weakens, dissipates, and eventually blends into background noise. But the appearance of Oumuamua, Borisov, and 3I Atlas complicated these assumptions. These visitors demonstrated that physical transfer between stellar systems is not rare, and that solid bodies, whether natural fragments or manufactured artifacts, can survive million-year journeys across the galaxy. If nature could scatter mineralogical and organic matter from one system to another with such efficiency, then technologically advanced species would almost certainly be capable of doing the same, perhaps more deliberately, more precisely, and across greater temporal scales. This reframing transformed the paradox from a question of absence into a question of detection. If extraterrestrial civilizations preferred to send physical messengers rather than ephemeral radio signals, then humanity's search had been pointed in the wrong direction for decades. Radio waves fade, artifacts persist, a crafted object engineered to endure cosmic radiation, micrometeoroid impacts and deep-time entropy could drift through interstellar space long after its creators vanished. The silence then might not be silence. It might be the hum of unrecognized information embedded in materials we have not yet learned to interpret. With this perspective, the anomalous characteristics of Oumuamua took on renewed significance. Its extreme elongation, its non-gravitational acceleration without detectable outgassing, its unexpected photometric behavior. Each trait became a line of inquiry rather than a curiosity to be minimized. Natural models remained possible, even plausible, yet the deviation from known physical categories invited a broader spectrum of hypotheses, including the technological. Under the silent cosmos lens, this was not speculation for its own sake, but a recognition that the boundary between rare natural processes and engineered structures could be far subtler than conventional frameworks allowed. Statistical analyses strengthened this view. If interstellar visitors passed through the inner solar system with measurable regularity, perhaps dozens per decade, then even a minuscule percentage of artificial artifacts would yield detectable examples over time. The absence of clear technological signatures might simply reflect the infancy of human detection capabilities. Instruments designed for comets and asteroids do not necessarily reveal the hallmarks of advanced engineering. A probe constructed from unfamiliar alloys or optimized for low reflectivity might appear indistinguishable from an exotic natural body at typical survey resolutions. Technology from a civilization millions of years older than humanity could operate on principles not easily recognized, much as a 21st century circuit board would appear inert or natural to an ancient civilization lacking the conceptual lexicon to decode it. Thus, the paradox softened. Instead of "where is everybody?", the question became, what forms of presence are we trained to see? The galaxy may be filled with signatures, structural, chemical, or dynamical, whose artificial origins remain hidden behind scientific assumptions inherited from an earlier observational era. And unlike radio signals, which require timing intention, and reciprocity artifacts require nothing of us, they travel on trajectories shaped by celestial mechanics rather than communication strategies. They wait silently for a moment of recognition. An even deeper implication emerged from astrobiology. If organic molecules were routinely exchanged between stellar systems through interstellar debris fields, then the seeds of biology might not be confined to any single planetary cradle. Amino acids, carbon-rich compounds, and crystalline structures capable of templating molecular complexity could disperse throughout the galaxy in patterns defined by gravitational drift rather than biological agency. Life in this view becomes not a rare planetary accident, but a galactic phenomenon shaped by dynamical processes far older than Earth. The paradox of alien silence might not reflect the scarcity of life, but the ubiquity of it. A quiet, diffuse presence embedded in dust, ice, and mineral matrices traversing the interstellar medium. In observatories across the world, researchers approach this reframed paradox with growing humility. The arrival of 3 interstellar visitors in rapid succession acted less like a revelation and more like a gentle correction, reminding humanity that the galaxy is not empty, nor indifferent, nor inaccessible. Instead, it is permeated with motion objects drifting across epochs, carrying with them information older than Earth's oceans, older than its continents, older than the biosphere itself. The question that once sought audible voices from the stars has evolved into a subtler inquiry about the material traces of distant intelligences and the silent stories embedded within them. And so the paradox continues to dissolve into something quieter, something more aligned with the rhythm of cosmic time. Perhaps the universe is not speaking loudly. Perhaps it never intended to. Instead, it leaves traces, fragments, visitors, wanderers, and waits for young civilizations to recognize that communication need not resemble conversation. In this softening of expectation, a new understanding emerges. We may not be alone, not because the stars shout their presence, but because their silence carries structure, pattern, and memory. And tonight, as telescopes continue to watch the sky, the question no longer echoes with urgency. It drifts like starlight across vacuum, becoming something gentler. What else have we already seen without yet knowing how to understand it? As the paradox softened into a slow, reflective question, the scientific community found itself navigating not merely data but the architecture of its own curiosity. Each interstellar visitor carried with it a quiet friction between established theory and emerging evidence. A friction that did not burn but warmed, inviting deeper contemplation. In laboratories, observatories, and conference halls, tension accumulated not as conflict but as a subtle, gravitational field drawing researchers toward new frameworks of thought. For decades, astronomy had lived comfortably within the domains of planetary formation, stellar evolution, and celestial mechanics. But now the discipline was being asked gently yet persistently to widen its aperture. The anomalies that accompanied the first visitors did not demand panic. They demanded patience. Oumuamua's improbable geometry, Borisov's chemically exotic coma, and Atlas's early activity created a triad of case studies that resisted simplification. Natural explanations remained possible, but each required invoking edge conditions seldom observed elsewhere. Extreme fragmentation, rare materials, or thermal dynamics operating under unusual constraints. This accumulation of exceptions revealed something about scientific culture itself. The instinct to preserve established paradigms to secure continuity of explanation was strong even when evidence gestured toward the need for reinterpretation. Yet this hesitation was not a weakness. It was the discipline's way of safeguarding sobriety, ensuring that hypothesis remained tethered to observation rather than speculation. Quietly, however, a secondary movement began to form within the discourse, a willingness to treat uncertainty not as a defect of knowledge, but as an essential component of exploration. Researchers started framing anomalies not as puzzles to be resolved quickly, but as invitations to expand theoretical space. The possibility of artificial structures, once dismissed as imaginative, excess entered conversation not as conclusion, but as one vertex in a multidimensional hypothesis field. It sat alongside natural fragmentation models, exotic ices, non-sublimating volatiles, and radiation pressure interactions, forming part of a spectrum rather than an outlier. In late-night discussions beneath dome shutters, astronomers found themselves acknowledging a humbler truth: the universe may have categories we have not yet learned to name. This quiet shift had methodological consequences. Instruments originally designed to classify comets and asteroids were now being evaluated through a broader lens. Could spectral signatures reveal engineered materials if such materials existed? Could anomalous light curves hint at hollow structures or composite geometries? Could non-gravitational accelerations be caused by mechanisms other than sublimation? Perhaps by ultralight surfaces interacting with photon flux? None of these considerations required abandoning natural explanations. They simply expanded the conceptual bandwidth through which data could be interpreted. Theoretical astrophysics absorbed this widening perspective with equal subtlety. Models of planetary system evolution were recalibrated to incorporate more diverse pathways of debris formation. Simulations began testing previously unconsidered configurations, objects shaped by tidal sculpting near compact stars, fragments produced by collisions within ultra-dense stellar nurseries, and aggregates formed in high radiation environments where chemical bonds behave differently from those in our solar system. With each iteration, the anomalous properties of the visitors became slightly less surprising, not because they were understood, but because the universe was being granted the complexity it likely possessed all along. Amid this scientific broadening, a quieter philosophical tension emerged. How should a young civilization interpret evidence that could point toward intelligence? The question was not approached with fear or sensationalism, but with a meditative sobriety shaped by cosmic scale. If artifacts from other civilizations existed, they would be ancient, perhaps older than the human species. They would be shaped by technologies with principles unfamiliar to us. They would not announce themselves, they would drift indifferent to our discovery. The challenge then was not to identify intention, but to recognize unfamiliar structure. This recognition required a certain humility, a willingness to admit that not everything strange must be immediately classified. In this context, debates within the scientific community became less polarized. The dichotomy between natural and artificial explanations began to soften. Researchers spoke instead of information density, thermodynamic signatures, structural coherence, and energy interactions. Under this framework, an object's origin could be analysed without prematurely assigning agency. A fragment exhibiting ultra-low density might be compared to both porous cometary aggregates and hypothetical light sail architectures. A stable tumbling pattern might evoke both collision, altered rotation, and engineered mass distribution. This approach preserved scientific rigour, while allowing imagination, not fantasy, but disciplined wonder to re-enter the analytic process. As these conversations unfolded, another realization took shape. The next discoveries would likely be different still. Interstellar visitors did not adhere to familiar categories. They represented a continuous variable population shaped by billions of years of galactic evolution. The three we had already observed were not anomalies. They were glimpses into a distribution we had only just begun to sample. A single object might reflect the conditions of a long-extinct planetary system. Another might carry signatures of a star that never formed planets at all. Each visitor became a data point in a cosmic census far grander than the ambitions of any individual observatory. In the face of this expanding horizon, scientific tension dissolved into something more peaceful acceptance. Not acceptance of ignorance, but acceptance of scale. An understanding that the galaxy's complexity exceeded the confines of any model, and that our role was not to master it, but to observe it with care. The anomalies of the visitors no longer felt like disruptions. They felt like the universe's quiet reminders that discovery is not a straight line, but a tide advancing and retreating, reshaping understanding with each new arrival. And so the scientific community continued its work not with certainty but with steadiness. The telescopes hummed. The models evolved. The debates softened into contemplation. Above it all, interstellar objects continued their ancient trajectories unbothered by interpretation, carrying with them the stories of distant systems and forgotten epochs. The universe in its silence remained patient, and the observers travelling through the night of their own inquiry learned to be patient with it. As new theoretical frameworks settled into place, attention turned toward the instruments that would soon reshape humanity's relationship with the sky. If the first visitors had revealed how little we truly perceived, the next generation of observatories promised to widen the aperture of our cosmic awareness. In the high dry air of the Chilean Andes, engineers ran final calibration sequences on the Vera C. Rubin Observatory, an instrument not merely designed to observe the universe but to listen to its faintest motions. With an 8.4-metre mirror and a camera of unprecedented resolution, it would scan the entire visible sky every few nights, capturing transient streaks of light that older surveys would have mistaken for noise. Its purpose was quiet but revolutionary: to map the dynamical flow of the solar system, with enough sensitivity to recognize patterns belonging not to planets or comets, but to wanderers from distant stars. This shift from occasional detection to continuous monitoring marked a turning point. Earlier discoveries had depended on chance moments when an interstellar object happened to intersect the narrow window of an existing survey's cadence. Now detection would become systematic. Hyperbolic trajectories would be identified not months later, but almost immediately, their anomalous motion flagged by machine learning algorithms trained on the subtle deviations that distinguish interstellar visitors from native debris. What once was serendipity would become routine. The universe for the first time would be observed with the temporal resolution required to trace its wandering messengers in real time. The implications reached beyond astronomy. By expanding the catalogue of interstellar objects from 3 to hundreds, the Rubin Observatory would transform a sparse dataset into a statistically meaningful population. Researchers anticipated new distributions of eccentricity, albedo, rotation, state, and compositional signature, each parameter offering clues about the environments in which these objects formed. The galaxy long studied in broad strokes would begin to reveal its fine structure. The metallicity gradients between spiral arms, the dynamical history of stellar associations, the relics of past planetary architectures, all of these stood encoded in the surfaces, isotopes and trajectories of interstellar debris. To study these objects was to study the galaxy's memory, but detection was not enough. To move from observation to understanding, scientists envisioned missions capable of intercepting visitors during their brief passage through the inner solar system. NASA's Conceptual Interstellar Interceptor designs lightweight probes exploiting solar sails, gravitational assists, and pre-positioned launch trajectories represented humanity's earliest attempts to pursue cosmic wanderers at tens of kilometers per second. The engineering challenges were severe limited launch windows, immense velocity differentials, and the difficulty of instrumenting spacecraft for rapid response rendezvous. Yet researchers approached these constraints with calm pragmatism. The universe would provide many opportunities. Technology would evolve to meet them. In time, an encounter once thought impossible, direct sampling of material from another star would become a milestone of scientific maturity. These preparations carried philosophical weight. With every simulation, every trajectory model, every redesigned sensor, humanity was acknowledging a quiet truth: the cosmos is not distant. Its materials, its histories, its fragments drift continually into our gravitational reach. The act of studying interstellar objects was not an attempt to reach outward, but to better receive what was already arriving. This perspective softened the boundary between the solar system and the galaxy, revealing them as nested components of a single dynamical structure. The Earth orbiting the Sun was not an isolated outpost, but a node within a greater flow of matter and information. Even so, the anticipation was tempered with humility. Not every object would be solvable. Some would be faint, tumbling too quickly for detailed spectroscopy. Others would disintegrate as they approached perihelion, their compositions inferred only indirectly through transient dust signatures. A few might display properties that defied existing templates, extremely low densities, anomalous scattering behaviour, or structural coherence incompatible with known astrophysical processes. Yet rather than generating alarm, these anomalies would serve as reminders that discovery is not about resolving every uncertainty, but about recognising which uncertainties expand our understanding. With increasing observational precision came another responsibility: interpreting anomalies with care. The debate surrounding Oumuamua had illustrated the risk of conflating the unusual with the artificial. As more visitors were catalogued, researchers emphasised the need for methodological rigour. Artificial structures, if they existed, would likely be rare. Their identification would require evidence far stronger than unusual photometry or weak acceleration signatures. But the search itself was not speculative. It was a logical extension of scientific inquiry. To consider technological origins alongside natural ones was not a departure from rigour. It was an acknowledgement that the universe might be more inventive than any single explanatory framework. The next decade, researchers agreed, would be defined not by spectacular revelations, but by accumulation thousands of light curves, hundreds of spectromillions of orbital measurements. Through this mass of data patterns would emerge not the kind that announce themselves with dramatic clarity, but the kind that reveals structure through statistical quiet. A preferred size distribution here, an unexpected clustering of velocities there. Subtle chemical signatures pointing to stellar metallicities unlike those of the Sun. A rare fragment whose isotopic ratios matched no known nucleosynthetic pathway. Each data point would act as a faint marker, and together they would map the galaxy's hidden architecture. And beneath the growing lattice of knowledge, one awareness continued to deepen. Interstellar visitors were not messages in any deliberate sense, yet they carried information across vast distances and epochs, with a fidelity unmatched by radiation or signal. Their trajectories were not intentional, but they intersected with our world nonetheless. In learning to interpret them, humanity was not receiving communication. It was learning to read the natural script of the galaxy. As telescopes prepared for their nightly scan and spacecraft designs matured on digital drafting tables, the future of interstellar study no longer felt speculative. It felt inevitable. A quiet, steady unfolding. A new era of astronomy defined not by looking outward into distant space, but by recognizing what the cosmos had already placed within our reach. And somewhere far beyond the heliosphere, unseen objects continued their long migrations toward us, silent, indifferent, yet filled with the history of stars we have not yet learned to name. Tonight, traveller, we drift to the quiet edge of the story. Oumuamua, Borisov, and 3 Atlas have moved through our solar system like slow, deliberate whispers, reminding us that the universe is never still, never silent, only patient. As the telescopes dim and the data streams settle into their nightly rhythm, we are left with a simple truth. The cosmos continues its ancient work, whether we understand it or not. These visitors show us that the space between stars is alive with motion and memory, carrying fragments of distant worlds across millions of years to brush for a moment against our small corner of existence. And you, observer, are a part of this unfolding. Your quiet attention is its own kind of participation. Wonder is not a solution. It is a way of belonging. So as you prepare to rest, let the unanswered questions remain soft around you. Some mysteries are not meant to be solved tonight, only acknowledged beneath the slow turning of the sky. Rest well, traveller. Stay curious. The universe will keep watch,